Hey guys, right. I have been spending the majority of my time trying to learn how to make EQS work, among other things. But predominantly, I wanted to get my AI working very smoothly. Because for some reason, I've always had issue using AI perception, and I've never used EQS before. And it seemed strange to me that it was so initially very complicated, but it seems to be, I don't want to downplay it, but I mean, it is essentially less than 100 lines of code to get it working pretty well, minus a few odds and ends here and there. And I have also managed to get it mostly working in C++. There's only one sort of middleman bit that I can hopefully quite easily put into C++, and then I can have a full solution as like, here's how you do EQS in C++. But because this was a completely new system, I wanted to do this separately so you don't sit here and have to watch me muddle my way through it, because it wasn't that it was particularly complicated, it was mostly the fact that there wasn't much if any examples of C++ versions of that system. Not that I had to do it in C++, but the whole point is to do the project in C++, because then, you know, next time if somebody for whatever reason needs to do it like that or prefers to, then here's a working example, basically. So I'm going to jump right into this, and firstly, I suppose the best thing for this is just to show you what it does, because the AI perception is all about sight and sound, and I mean you can add in your own kinds of perception. If you wanted to add in smell, you probably could. I think you'd have to configure a custom thing for it, but it should in theory work in the same way that sight and sound do. An event occurs that triggers a perception update in an area, and things that can perceive at that distance get notified about it. It's kind of as if all your AI have like a sphere volume set to a certain radius, but you'll be able to see it now. So I've got this exactly the same as it was before. Now if you press apostrophe and then I turn off the AI and behavior, so if I put the perception on, you can see it here, it's numpad 4. So you can start seeing this ring. So the green ring is initial perception, so where it can see. So this is its sight radius at the moment. So you can see at the top here, there's category perception, it's got sight green, and then we leave line of sight if we pass this line. Now, I'm not 100% sure, at least in my game, whether or not these two would be different, and what my sight radius would actually be, because my game is going to be predominantly like a typical RPG. You walk around and you go around the corner of a wall and then you get attacked by some AI or something. So I'll figure that out. But you'll see, as soon as I go here, so obviously you've got all the shooting and stuff still. So you can see that my character is in line of sight and it's tracking my movement exactly, which is really cool. And then if I do this, so and let's see if I can remember. Nope. Let me pause. Eject. Okay, that's unfortunate. Let's do this from a different perspective then. Okay, now, That's unfortunate. Okay, so what you can see here is the perception system has found that here we've lost line of sight. So this is the last location that this particular AI has seen us, and its age is 0.61. I'm guessing that's like less than half a second ish. And then you can kind of faintly see it, but there's this grey line linking between me and that. So this is obviously pointing to what this and the engine calls this a stimulus. So this stimulus is linked to this target. So this is terminology you'll hear quite a lot going forwards with AI perception. But as you can see, the grey line always follows us, and you can see it's as soon as we get spotted, it gets updated again. And you know, the AI is always moving closer towards us. Now the perception system isn't what's controlling the AI to actually move and follow us. All the perception system is doing is telling us when we get line of sight, and then if we lose line of sight, where have they gone to? So if we were doing this with sounds, you could, for instance, play a sound cue over here, and the AI's sound perception can hear it, and then you can make them move towards the sound stimulus, which would be, you know, here, so they would come towards it. So if I was over here, threw a grenade here, and this AI couldn't currently see me, let's say they were over there, the sound would play, and the AI might walk over to come and investigate. So that's the kind of stuff you can do with perception, but it's only the triggers as to when perception is changed. So let's show you the code for this. So all you need to do is you get a AI perception component. You create this in the constructor. You then make a sense config. So this is like a data set for a particular sense. In this case, it's sight. So all of these sense configs inherit from a base class of UI sense config. And obviously sight has its own unique properties. So this would be like me creating the structs for all of the different weapon variants and things. But in this instance, of course, it's the configuration for the AI's sight. So then you run the configure sense, and we pass in our sight config. So that the perception component can have 0 or more sense configurations. So obviously it can be sight, hearing, smell, whatever. And so we tell it to configure the sense. So we give it that, a link to our sight config, and then we set the dominant sense as our sight. Now this is something I've not messed with, but I get the impression it's like a priority system, where if one sense is, let's think about this. So if you've got a character that's blind, or like let's say nearsighted, you might have the dominant sense as sound, and then just add sight as the normal sense. And my impression of briefly looking around the dominant sense stuff is the idea that it will prioritize updates from that particular sense. So they'll focus more on updates from their hearing over their sight, or something to that effect. Then we come into the main crux of this, which is the on-target perception updated. So this is when the component's perception triggers an update based on the sensors. So in our case, it's sight. And the whole idea of target perception is every time you witness or you experience, let's be more specific, every time you perceive something, be it sight or sound, your target perception gets updated. And the actor, so the perception always knows exactly where that happened and what caused it, generally speaking. And so this means that your AI can be as intelligent or unintelligent as you want it to be. So when we come into this, we get given the actor that caused the perception update. So in this case, we see the player, which would come in as this actor. And then the stimulus is the current information based on that actor's perception. Our current perception of that actor. So you have some very basic things. You've got the location where the stimulus happened. So that's what you'd see here when I do this. So this is now the stimulus location. So if I do that, so the stimulus location, the last update this AI would have received would have the stimulus location set to this, not this. So this means if you want AI that don't just blindly follow the player exactly where they currently are all the time. So let's say you had a horror game and you wanted the monster to run where they last saw them, you would use this stimulus location. And you can determine a few things, but obviously in my game there's only one thing I care about at the moment. So the was successfully sensed is determining whether or not the sense has been sort of, well, whether or not it's still active, let's say. So in our current case here, the was successfully sensed is false. So because we lost sight of the target, and we know their last location was here because we haven't sensed them again since. So if this were to run multiple times during this current situation, the last location would always be this, and it would come back as false because we still haven't sensed them again. In fact, if I go into here, you can see we see them. So our actor is the top-down character, which is our player, and our target is the same thing. So we're chasing the thing that we just saw. And then the stimulus for the actor, it was successfully sensed, obviously, because we just ran around the corner and we saw them. You can, well, you'll see in a second when I hit play. And so we can see them now. And that's all this perception does. Right, that's all you need to use this for. This is just do we currently have line of sight on the target? Yes, no. And all this does for me then is hook into my environment query system, which I'll explain briefly in a minute. So if I hit continue, we pick them up again. So let's come into this, and I do that. So you can now see the stimulus. This is the first instance of where we don't see the player, and you can see that the player's stimulus location, this will equate to the green ring there that you can briefly see forming. And so we now know that because it wasn't successfully sensed, i.e. we have a target that's gone out of line of sight, so now we know we need to move towards them, which is what this is doing. Cool. And all you really need to know past this, and there's a few things I still haven't set up for this, but you've got the initial sight radius and the lose sight radius, which were those which are these two. So this is my sight radius, and this one over here is the lose sight radius. And like I said before, I'm not sure whether they need to be separate or not for my game. I'd imagine it's like you might lose sight of things sooner than your overall sight. I'm not quite sure the intended use of it, but yeah. And then obviously you can set the peripheral vision angle, which mine's set to 90 degrees. I don't know if it's supposed to be able to show that, but I would assume there's some vague vision cone coming out of here. Maybe you can show it, maybe you can't. I'll look into that sometime. For now, obviously, you can see that the AI initially can't see me. And then, you know, if I walk behind them, they can't. If I had sound implemented, I might make them detect sound as I move around from this distance or something, and then they'll turn around and shoot. Or if it was a stealth game, I might not bother at all. But you can see there, I walked past them and then suddenly they saw me. Now they don't. And I can walk around them for ages and they'll keep going here. So that's the AI perception system, as far as I've understood it. All you need to do is, I think this system, this detect enemies, friends and neutrals, I believe that's something I need to start utilizing so this works correctly. But then all you do is you register the UI perception system, and you pass in us, you get the sense implementation, and the pawn that is going to be using. So this is how you become a source of stimulation. So if we wanted other things to be seen, we would register this. So we'd register, like, I don't know, let's say we had deployable turrets or something. They would also need this to be the case, essentially. So yeah, I think that's everything there. I'm not sure why I'm doing this here again. Let me just tidy that up because it seems a bit pointless doing it in two separate places. Yeah, there we go. Should still work, I'm sure. Anyway, so that's AI perception, right? If you wanted hearing, you would come up here, you would create another default sub-object, and this would be underscore, is it some? It's probably, hang on a sec. Go away. Thank you. Right. Come here. I'll just find what they called the other one. Yeah, so there's hearing, there's damage, prediction, which I'm not 100% sure. I need to look into a lot of these, but yeah, you can see here there's AI sense, blueprint, damage, hearing, prediction, sight, team, and touch. They're all the built-in default ones, and I'm going to assume you can make your own complete customizable ones, which I'll do at some point, and that will be a completely separate project, but we'll see what happens, because it will be very interesting to try and make my own type of perception. Anywho, right, so EQS. The EQS is the Environment Query System, and it is used to gather predominantly, it works in the same way that the AI navigation works. So it gathers essentially like a score of locations between where you are and where you want to move, and it assigns a score based on those locations, and then moves through the optimal, like the cheapest path essentially. So like a path will have a cost, and it always moves through that the cheapest cost. What EQS does is it allows you to define, they call them tests, and they're tests based on a context. So to be very specific about this, if you, let's say you wanted AI to move towards a health pickup, like the closest health pickup to them, you would create a context which returns health pickups in the world. And then you provide that context to a test, and the test would be a distance check. And the lower the shorter the distance, the better score the health pickup will have. And therefore the AI can use that information to determine the closest health pickup and always move to the correct one. That's a really basic example of it, and it's surprisingly easy to implement. It just took me an extremely long time to make it work how I expected it to work. So I'm going to show you an example of this, what it actually looks like, because it's kind of hard to explain without visuals, because this whole thing is visuals. Right, so we're going to, oh, that's interesting. Yeah, okay, I think I broke this when I removed the thing down here. I'm curious as to why. Do I need to put it in twice? I can't imagine I do. Let's just make that work again. I'll put them both back if it stops working again. My bad. I'm surprised. I would have assumed I wouldn't need to put that in at the top here before it's even in use. But we'll see. So we hit run. Oh. How do I do this? How do I... okay, round 2. Alright, we'll put this in at the bottom here as well, I guess. I don't think I changed anything else. Let me just check. I moved that. Remove some spacing. That's all. Okay. Good, right. Sorry, round 2. Here we go. Oh, let me hide that. Okay, so that's same as before, but you press apostrophe. You probably want to turn off the behavior tree in the AI because it gets a bit much. And this is what EQS looks like. So what this is a grid that you define that has typically it will look like a heat map, a scoring system, but mine's more of a pass and fail system. So blue is locations the AI can't go to, and green is locations it can. And so as you can see, as soon as I leave line of sight, it recalculates all the possible locations the AI has to go to be able to see me. Seems to be a bit iffy for the moment, but there we go. This is a 1,000,000% improvement over what it was doing before I learned how to do all of this. So it takes a short while for the EQS to actually regenerate, but you have a context, and in my case my context is my player, and then you have a test, and the test is a scoring system based on the locations generated by EQS. So what EQS does is you define a grid, and this is the only part of it that is currently not in C++. So I think what is it, environment query? I think it's, artificial intelligence environment query. You then drag off of the root and you make a points object here. And so we've got a grid, a simple grid point system. I'm not sure, I haven't tried any of the others yet, so we'll see what happens there. Because I would imagine perceived actors might be an interesting concept to look into. But for now we have a grid, and you have these properties. You set the size of the grid, the space between the grids, the points in the grid. As you can see, it's all very neatly represented across there. And then you give it the context. So this is what it generates the grid around when it determines the point system. So you can very clearly see it generates around the center of the player. If I do this, so you can see, obviously the point we're closest to is probably hidden under this, but you can see it clearly generates in an area around the player. So as we move, and as the target, as we move out of line of sight, you can just see it very smoothly recalculates optimal AI locations. And it's really cool. So to be honest, this is wonderful. Exactly what I was hoping for. So what we have then, so I've custom made my own context. So this is just a simple C++ class that inherits from the context AI's EQS context. So let me just find enemy context. So we have this find enemy context. So all I did was go into C++, classes, right click, new C++, go into the usual classes, type in context, or well, probably a bit more specific. Oh, hang on, no, it's environment. Environment query context. Make one of those, and then you get presented with, obviously an empty class besides all of this. And then we just want to override the provide context method. As you can see, it has a query instance and context data. And so this query instance and context data will be, this is our query instance, the EQS find player. And the context data is so that we can add potentially multiple contexts to the data overall. So you run the base class version of provide context. I'm still not sure if we need to do this. I'm going to assume so. We'll find out later, I'm sure. And then all you do is you get a reference to the thing that you want to provide context for. So in our case, we have a location. So we're going to provide to the query instance a point, and our point is going to be driven or is going to come from our AI controller. Now the AI controller we can get from the query instance.owner. This owner will be is that right? I'm casting to an actor and then also casting to a controller. Oh yeah, I see. So, I mean, if I was to do this in a bit more of a specific way, owner, we're going to do that. So I'll just write this out a bit more neatly. There we go. And then we can go owner.getInstigatorController. Though why I can't do get. Okay, that's interesting. Return the. That's interesting. Okay. So then we get the controller for the actor, which we can guarantee is going to currently is our A-base AI controller. So we now have a reference to the controller. We get the target from our controller, which is stuff we're already setting based on the perception, which I'll show you in a second. And then we want to add to the context data a single item point type of point, and then we get the last known location of our target, basically. So from the AI controller's perspective, we come into here. So we don't have a target, so we cast the actor that we perceive. We check whether we're enemies with them. If we are, we set our target, set can see true, and then obviously we're doing this on-screen debug message, which I don't actually need to represent anymore. So we'll just bat those out at the moment. And then, so that's when we initially see the target. And then typically what we do is if we lose sight of the target, so if can see is false, which comes into play typically here, we will update our last known location and we will run the query. So whenever we don't see our current target, and as long as we're not already moving somewhere, we update the last known location to the actor's location. This is on tick because we're not making a game where we just move to the last known location like this. I need to faff around with this a bit more, but for now we basically constantly update the actor's target location, and then we run our query. So what we have is a query request, and this is something that is it's a sort of a generic object that you pass in the query and who owns the query. And then we subscribe in a similar way to the what am I going for? In a similar way to the sort of query updated. Let me think about this. It gives us a sort of an event driven system. So let me just find it. Yeah, so when we execute the query, we have a reference to the query we want to run. In our case, it's our find player query. So in begin play, we load our blueprint query and then assign my query to the one we find there. And then whenever we execute it, we tell it it's a single result query. So we're only looking for the most beneficial location. And then we give it a callback method, in which case this is our my query finished. I'll rename these to something a bit more specific now that I know how it works. And then if the result is successful, so we've got at least one location which doesn't have a failed score, we get the item 0. So this is get the first and in theory only item as a location. And then we just move towards it. So I know that was quite a lot, but I'll go through this step by step. So our find enemy query context. So this is going to be this is run every single time the queries run. So it will get the AI controller's last known location every single time we run the query. So obviously it will have the most up-to-date data. And then this is where it gets very complicated for a bit until I can explain it well enough. Okay, so we've got a player, we've got an AI. The AI perception system sees something. So we're fine. We don't need to move. We've seen our target. We're good. So if we come into the controller, when we stop seeing our character, this is where can see becomes false. So we lose line of sight. We run our query, having updated the last known location, and the query runs. It finds suitable locations that would have line of sight on the last place we saw the player, and then it moves the AI to it. So we run the query, we get our get the last known location. This then comes into this code, which is a lot, but it's actually reasonably easy to understand once I go through it. But we run this. This is the code that basically figures out where the good locations are and the bad ones are. And then we come back into the controller with the finished query, and we go get item as location, and that's the location that will have line of sight to our player. So I run this, do this. So I'm going to pause it like here. Right. So what we have here, these points are referred to as items. They are items in a list generated by the grid we've made in this find player EQS query. So what we get in the code when it comes through into our test, so this is an environment query test, which I need to rename because I repurposed it after I initially made it. So we make a query test. You go into here, do the same as before, C++, here, all classes. And then you find environment query test, which is this one here. And once we've done that, we can assign it to our query here, this one here. So you can see we've got weapons distance test, and that text, just to show you what some of this does, that text is defined here. You can see weapons distance test, which gets pulled through into here. And these have a plethora of attributes. You do have to assign the context to these tests again. And I will need to look into that again at some point to really iron this out and only use the bare minimum stuff to make this work. But then our test gets run, and we get given this list of points as items in an array. So if we come into here, so a lot of this is reasonably straightforward distance checking code. I just separated a lot of the properties to make it more human readable for now. So what we get is this run test. So we want to get our query owner, which in our case is going to be the AI controller. We then have this set of context locations. So this is just an empty array, but we essentially want to get the list of locations that were given to us by the grid. So all we do is we prepare the context. So we pass in our context, which will, in our case, we know it's going to be our find enemy query context. So the context will actually be this vector here, which gets passed in there, and then based on that vector, it generates the grid you see here, based on the grid settings we defined in here. So then this is an out parameter, so it populates this array of vectors, which is something we can iterate over. Right, sorry, it generates, it gives us the current location. So this will be the player's location. So we know that it's only ever going to be one, and the first one will be the AI's the AI's last known location. Then what we do, sorry, I was wrong about this section. This isn't the grid that gets generated. This section is the grid that gets generated. Right. So we have our query instance. Our query instance has a list of items. So if I go into this, right, item details, which is, there's item details here, I believe. Pretty sure that's all there is. Yeah, looks like it. Cool. So this is the grid. Then we create an item iterator, and we pass in our query test, which is this, and our query instance, and this creates a for loop. So this is basically for every item inside the query instance. Now we know that our items are locations. I believe they can be other things like the perception and stuff. So you can see in here, we know that this is a grid and that it's a grid of locations. Whereas if it was perceived actors, it might be an array of actor. or composite might, I don't know, produce some other kind of query instances. So now we have one of these locations. So this vector equates to one of these, presumably the top left one, probably off the screen here or something. And then this is where you can do basically whatever you like. So all of this code in here is essentially me manually figuring out whether or not a location is a viable place for my AI to move to have line of sight onto its target. So you can see here, I check if we've got a weapon. We should. It would be crazy if we didn't, but just in case I do. I then check the distance between our target location, which we pulled from our context. So this will be the AI, the player's location for now, but later on it might be another AI's location. We then get the weapon range. We then check whether the distance is less than the range of our weapon. Then if we're in range, we do a load of other calculations, but this is the important section. If we're not in range, we come down to this else here. So let me collapse that. And this is where you start doing the scoring system. So each of these points has a score assigned to it and a pass or fail potentially. So in our system, anything that is out of range, regardless of whether we have line of sight or not, is considered a fail. So as you can see here, there's this very distinct line, probably these ones here, that are all failures, and everything past this is considered a failed location. And that's of course because the locations are out of range. But then you can see some of these inner points, some of them are green, some of them are blue. And these are the ones where I determine line of sight, which is all this. So I did something which I think was the appropriate means of doing this. But essentially, we need to add to the Z location of these grids. So each of these gets their up-downness added to, so that we can start tracing from, as you can see in here, half the height of our character. So we're making a sphere trace, so we're going to make like a circle that then gets emitted out towards our player's location to check for collision. And obviously we want to consider that we're colliding with things if we're approximately half our height upwards. So we could still technically see the player from behind low walls or something and still try and shoot at them. So that's what this is for. We then do, and I've made a macro for this because seeing all of this all the time gets a little obnoxious. If I put this on for oh, hang on. Really? Hang on a sec. I just need to find the debug types for one frame. Yeah, I was close. That will just turn debug on so you can see exactly what's happening. So this is doing a sphere trace. So we are sending a sphere, a collision sphere, emitting from us out to the, from one of the locations in the grid directed towards the player's our target's current location. So if I do this, There you go. You can see. Let's. I need to always pause now. Damn it. I used to have that as a button. Oh, that's unfortunate. Oh, pausing it makes the debug go away. Anyway, so what you can see here now is this is my sphere trace. You can see it's quite large, and more importantly, it's emitting from just above the ground, and it's about the same dimensions as the character itself. So you can see this is a pretty sensible location to check. If we collide with anything there, then we probably can't see the player anymore. So that's what that's doing. So you can see, you can just see that all the collisions are coming from all of these different locations, which if I turn EQS on, it matches the grid locations. And because it's only the ones in range, in fact, this is excellent that it's sort of bugged out here. You can see that you can see it's now going above every single location here and drawing a line trace to our player. It's interesting to me that this hasn't moved the AI for some reason. But yeah, so you can clearly see it's going through all the locations, and all the red ones, of course, are ones where it's colliding with something else. So that's what we're doing here, and all we're doing is we're looping through here. If it's a blocking hit and it's not our target, so we haven't collided with our target, then we're going to assume we can't see them, because if it's anything other than the thing we're trying to attack, then we probably can't see it. And therefore we can see. If it's false, yet again, we set the location to a failed state. So we set that item, which obviously represents the location in the grid, to failed, and give it a score of 0. Whereas if it passes, what I'm doing here is getting a percentage check based on the location's distance from our AI's distance based on the range of their weapon. And what this is essentially doing is generating a score that gets that's higher the closer the item location is to the AI's current location. So if you see, I'm not sure why it's bugging out in that there. So what used to happen when I didn't do that was the AI would move to the first score in the list entirely. So rather than moving the shortest distance to get line of sight to the player, if I show you, that's pretty cool. If I show you this, so if I move here, what used to happen is the AI would move somewhere over here or even up here whilst they're down there. And so I needed a means of scoring items that were closer to the AI's current location higher than those further. And that's what this does. So I think it does that anyway. It's going to be, again, it's going to be something I'll need to work out, but it seems to work is the point. It stopped the AI from running halfway across the map to try and find me all the times. Now obviously as usual, I'll leave all of this code online and I'll keep improving it, and this might be reworked several times over, but it's a nice, fairly clean example of how to do EQS, at least the basics of it inside C++. So once I get a lot better acquainted with it, I'll document this and I'll maybe do a full start to finish guide on how to do it and how to use the other types. Because I cannot find a single other person who has done EQS in C++ other than one of my friends. But I think that would do for now, because that's all I've got going for this at the moment. But as you can see, my AI has massively improved since I've done this. They don't get stuck on things anymore. Let me just redo this real quick. Just so it doesn't do the debug. I think sometimes if you have lots of debug lines active at once, particularly with line traces, it does tend to slow down the processing, because as you can see here, it's still there's definitely a situation when you get too close to the AI, like here. I'm not 100% certain as to why none of these would be valid. Oh, I know what it is. It's because my model is way too close to the static mesh. So if I do this, all the collisions from the sphere are going to be hitting this as well as the player. So I'll need to investigate a solution to that. I think my initial solution to that would be to check if the player's model is currently colliding with the thing that I'm hitting inside this collision check here, this bit here. Perhaps check the order of hits. I have to see about that. Hang on a sec. Right. Goodness me. But this is a really good start, and after I've refactored a lot of it, renamed some things, ironed out problems in here, this will probably be a very solidly working bit of code, basically, in theory. In fact, tell you what, let's just briefly do this, because it will take me a few seconds. My intention here okay, so what we're doing here is checking if we've hit the actor, and because this is going to loop in order of the position of the line trace, so the point that we're looking from to our target. If we hit something and it's not the actor first, then obviously we can't see them. Otherwise, if this is true, as in the thing that we're hitting is our target, then it doesn't matter what else happens afterwards. So let me show you this. That's more like it. So if I do what was breaking it, so this was fine before. We can walk around here, no problem. But if I do this now, yeah, he'll run straight towards me. There you go, simple, quick EQS fixes. Oh, that's interesting. So it's still a little buggy. I'm curious as to what's happening in that instance. Because some of these locations... So right now, you shouldn't need to move at all, so I don't know why he's bothering. Oh, I'm stuck. Oh, we're inside each other. If I move here... still a little off. I'll have to work on that, but see, the advantage is now I can work on that. That's the whole point of this. I can improve this and know that all of my AI are going to be affected equally by it, and once I get this working, we're good to go. I should have some very functional AI. Right, so I'm going to stop this here because it's been an hour. I was kind of hoping to do it in half an hour, but then I forgot how complicated the EQS system is to even talk about, let alone to actually get working. So, but yeah, I fully intend to do another video with a lot, probably even scripted video of like a how-to guide or something, because I'm probably going to be the first person to do that for this. Outside of blueprints, so yeah, I'll look into that. So yeah, thanks for listening if you did, and I will carry on. See you guys around.